As Lasha said, I'm Will Lang from NC State, and today I'm going to be talking to you about my student Al Gorski's final chapter of his dissertation. Al graduated a little while ago and unfortunately wasn't able to make it today, so you're stuck with me. So one of the big changes we've seen as we move to mobile platforms is the idea that applications are security principles, and there's an enormous amount of security benefits to this change. I could probably go on for 10 to 15 minutes on this topic alone. And if you're interested, I gave a keynote talk at YSEC over the summer on reflections of a past decade of mobile security research. That talk is online if you're interested. But the context I want you to have for today is that when you make application security principles, there's a significant amount of onus placed on the operating system to ensure that that enforcement happens. And so we've seen research in different areas over the years looking at the Android platform itself. Back in the early 2010s, there was P-Scout and Stowaway that were designed to map the APIs that applications are calling to the permissions that correspond to them. More recently, there was a cluster of papers that looked at the hard-coded access control checks inside of the Android framework to determine whether or not they were correct. So when you have an application, make a call into the framework, there's a bunch of conditional logics, if-else statements looking at permissions it should have, looking at UID values to hard code in there what is allowed to or not allowed to access that RPC entry point. And so all of the work we've done studying applications and looking at their permissions, it doesn't matter what permission they have if you get this part wrong. And so these works looked at the correctness of these checks and actually used consistency as a proxy for correctness. And the idea was that if you have two different entry points that go to the same protected operation, they should have the similar or the same access control checks. And we had a paper called AC Minor as part of this sort of area research a number of years ago. After we finished AC Minor, we looked at the ways in which these entry points called one another. And we found that it was actually highly interconnected. Lots of these entry points calling lots of other entry points, and you see the interconnected graph on the right side. And what's interesting here is that when one entry point calls another entry point, frequently it's changing processes. And so when you change the process, a lot of these conditional checks that I mentioned, right, they're checking based off of the PID of the caller, what's the UID, what are the permissions associated with that. And so you lose the provenance of that initial request, which application actually called that. And this can lead to different types of confused deputy vulnerabilities. And so here you see on the slide, you have a third-party application. It can't normally call entry point E2, but it can get there indirectly through E1. Now, these deputies aren't inherently bad. Actually, any modern operating system that's going to gate access to sensitive information, they need to have these deputies. It's a part of what's there. But this is a place that can be problematic that we need to study more deeply. And that's what we created the Android Re-Delegation Finder, or ARF, to look at. And as part of that, we created a number of heuristics to sort of move away the more common this is okay scenarios. So after we did AC Minor and ARF, we looked at this and said, okay, these access control checks that are happening at these entry points. What else can we compare this against? What about files? Can we look at the files and find a similar type of redelegations happening there? So if you interpose these two different figures I just showed you, and now you have applications calling into the framework, there's permission checks, UID checks happening there, and then there's more checks happening into the Linux layer itself, and we can have the emergence of a new type of confused deputy vulnerability that can happen here. Now, again, these deputies are inherently, they need to be there. Just because there's this redelegation doesn't mean that it's actually bad. But our hypothesis is, similar to what we did with ARF, we can programmatically remove a lot of the cases that are safe. The cases that what makes it safe versus not safe, what sort of sanity checks are deputies doing, is very service specific, and programmatically removing all of that is very hard or maybe impossible to do. So we created FReD, the FReD File Redelegation Finder tool, and the idea here is that we're going to find where those entry points are. We're going to figure out what files, which of those access files, and for the files that are accessed, what are the file paths, and for those file paths, which of those are sensitive, and then which ones of those are redelegated. So we did this with static program analysis, primarily in Java, and so we looked at the Java system services. There are purely native ones like the camera service we excluded, but the vast majority of the system services are written in Java. We did extend that analysis into the native code, so through the JNI layer, we extended our analysis to look at this as well, thinking that, well, maybe there's some interesting low-level files that are accessed in JNI that we want to reason about as well. And of course, we built on top of the AC Minor and ARF tools that we created previously. So here on the right, you see a sort of a mock control flow graph. And so you might imagine that the straightforward way to do this is you're going to walk forward in the control flow or call graph of this analysis, find the file methods, and then do a backwards data flow analysis to resolve what are the strings. And so conceptually simple, but anyone who's actually written these tools knows that when you actually try to do this, it's significantly more difficult to accomplish. The first thing we found was, what do we actually want to use as those file methods? And so you might think, well, there's these clearly defined JNI interfaces for accessing files, and these are the things that I annotated a decade ago with Taintroid. But we found is if you do your backwards data flow analysis from those, you lose a lot of precision in deriving the strings. There's a lot of interesting control flow and abstractions that happen, or various extra strings might come in. What you really want to have is, inside of the system service, you want the instruction call that's calling a file method. And so these JNI methods there's Java wrappers around those. On top of those are Android wrappers. And so we want to identify what is the highest level semantics of file method that we can then do that backwards data flow analysis from. So we did a semi-automated approach to sort of snowball out to those methods, starting from the 360 JNI methods out to over 2,000 of these. The next step was figuring out what are those strings. And so we created an intermediate representation to capture the ways in which these strings were combined and constructed together. Something that was really important here was the environment variables and system variables, that we could figure out what the key is to do that lookup, but we couldn't resolve the whole path as part of the program analysis, so we were then able to post-process and combine this together. We also did this analysis in the native code. We didn't have to go to the intermediate representation in the native code, which we did with Anger, right? Just propagating the strings, and gave us those values. It was much less complex in that space. Ultimately, what we did was derive regular expressions from this that we could match against files. So we took these regular expressions and we took files off of a real device, and then we took the access control policy from those files and said these are the ones that are sensitive, they're owned by system, they should only be read or written by system processes, matched those up, got our sensitive files, took the access control check semantics that we had from AC Miner and compared that and did that re-delegation analysis and said, okay, there's some re-delegation that's happening. Remember, so two things here. One is we needed to get files from a real device because many of the files of interest were in /data. And so tools like Big Mac that can derive files from an Android system image, they're getting from other places, but not the stuff in /data. You need to boot the phone up to get to those files. And the other thing was that remember that these deputies, they're not inherently bad. We need to refine them down. So we studied 3 different firmwares. We actually started with AOSP 9, and then over the course of the project, had to port it to AOSP 10. That process took a matter of hours to redo some of the manual parts of finding those file methods. And you can see a lot of details here in this, a lot more details in the paper describing this. Some things to note here, as you'd expect, AOSP and Google were very similar in terms of the counts of these. Samsung added a bunch of code. Interestingly, the number of file methods stayed about the same both across different versions and across different devices. We could also see that Samsung added a number of additional entry points at access and sort of access files. We have a number of heuristics to kind of refine ourselves down. Details, of course, in the paper and that. I can't go through all of them now, but we had down to around 23 that we actually needed to manually inspect and dive in. So sort of confirming that hypothesis that I mentioned earlier. So doing this analysis, we went and inspect these. And so when we did this, so a little sort of note on the refining down. So what we would do was we look at those and say, that's a general pattern. Okay, we programmatically remove that and sort of remove swaths of these. We came down to eventually 12 different cases that we thought were vulnerabilities, of which we received CVEs for 5 of them. So you can see they range from data manipulation to data leaks to denial of services. One of the interesting ones at the bottom were these Samsung ones. These were actually the only case that we found anything in native code. We originally hypothesized we really need this native code analysis because there's going to be all of this interesting file manipulation happening, and it turned out, at least in the JNI code, that wasn't the case. This was a binary. We couldn't reverse engineer it really well, but we could look at the Java portions and say that based on the access control checks and based on a named blockchain TZ service, blockchain trust zone service, that seems kind of interesting. And so we sent our suspicions off to Samsung, and they confirmed that it was indeed a vulnerability. Also noting, all of these ones that say AOSP, we also saw those same vulnerabilities in the Google and the Samsung firmwares. So just to show you a little more detail here, so this is the first CVE that I mentioned. So this is the removed shared account user as user entry point in the account manager service. And here an account is Facebook or Twitter or Google account. And you can see that in this entry point, there is indirectly this access to this SQLite database file. And you can see here there's some abstraction that's happening, right? So the ACS accounts DB, delete shared account, right? Going from there all the way down to those actual JNI methods that they're doing. There's a lot of control flow analysis how to get you down to that. But what we ultimately do is inside of there figure out what was that string and trying to resolve that. That's the regular expression for that path. This is also a good example because it shows you that if you want to try to programmatically identify what is the bad redelegations that are happening, that's hard to do. In this case, it was missing a call to is account managed by caller, right? Which is really semantically associated with that specific surface, right? That's the safety check that this was going to do. And the flaw here was that any application could go and manipulate the account information for some other account. So Facebook could go and manipulate to Twitter, for example. And so this is a subtle flaw that you can identify by honing in on these. Just a high-level overview, limitations of things you might expect. I mentioned the stuff in /data. We need a real device in order to get that information. We're focused primarily on the Java system services. We didn't look at the native system services. We also were looking at the ones that were directly called, and I think there's a little bit of fruit on the tree here if you think about how you call a binder interface and it returns a handle and that has other ones. We didn't sort of dive down into those, so I think it could be extended into those as well. And of course, all of the limitations you'd expect from building on top of static analysis tools in terms of the precision. We did go into the native code, but there's all other sorts of limitations and limitations with AC minor as well. So I'd like to thank you for listening to my talk. We've got our source code online and be happy to answer any questions.
Great.